Hey, this is Baylor. I wanted to show you some submesoscale and Langmuir movies. And these movies are actually going to be drawn from the same simulation, which is the one that's shown here in the movie. And it's described in the paper at the bottom of this page. So it's a fairly standard, these days, submesoscale simulation showing temperature, warm temperature region benched between two colder temperature regions in a periodic domain. You can see what sneaks off on the left comes back in from the right. And we're looking from above in the upper panel and from the side in the average along the domain from the side. The direction of the wind and waves here is creating an Ekman transport in the boundary layer. And the boundary layer is about 50 meters deep, as you can see from the labels on the side. The front where cold water is being brought over warm water by the Ekman transport is unstable to mixed layer eddies. A submesoscale baroclinic instability, which you can see here forming the swirly patterns. The front where the warm water is being brought over the cold water doesn't appear to be unstable to these same features. But this is a high resolution simulation, so let's zoom in and see what's going on smaller scales. When we zoom in on different frontal regions and other regions in between, you can see that there's a diverse kinds of interaction. There are also much smaller scale features which we couldn't see in the global zoom out that we can see when we zoom into these 1 kilometer by 1 kilometer regions. Let's go one more step and then I'll explain a little bit better what's being illustrated in these zoom in regions. In this zoom, what's being plotted are surfaces where there's a large vertical velocity colored by the temperature. So what you are seeing are actually the convergence zones, the windrows between Langmuir cells away from the temperature gradients, and then a frontal structure which also has a large vertical velocity down the nose of the front, which is also shown here in the gradient colors, which is indicating the temperature associated with the front. As you can see, both the front and the Langmuir cells are aligned with the wind and wave directions. And the paper at the bottom actually explains how there are similar Stokes forces involved in both the generation of Langmuir cells and the generation of strong downwelling at fronts. We think that these have a common genesis in the nature of the surface wave Stokes drift interaction with a turbulent flow beneath. If we go to a different front, which is not aligned with the wind and waves, you can see that it's much weaker and there's not as much of an interaction going on at the surface. In fact, you can see that some of the features are kind of overflowing the others and seem to pass more or less through this front. If you look at all the 6 fronts that were highlighted, or in fact, there are about 15 fronts or so that you can pick out from the bigger simulation, only the ones that are flowing down the Stokes drift direction are strong. So we think that's the key factor for the Stokes force strengthening of fronts. Of course, there are lots of other interesting interactions that are going on between the submesoscale and boundary layer, or Langmuir turbulence in this case. And there are lots and lots of different simulations that show different kinds of interactions. There's a lot more to do to understand them better. Thanks.